All right, guys, so we're going to talk about logarithmic functions. So the first thing I want you to know is that logarithmic functions are inverses of exponential functions. If you remember, we just covered exponential functions, so now we're going to go ahead and do logarithmic functions. So let me start off with this. So let's say we have y is equal to 2 to the x. There's our exponential function. So if we wanted to write the inverse, well, the inverse would be x is equal to 2 to the y. Remember, when we find inverses, we just switch the x and y value. Well, in log form, we write this as y is equal to log to base 2 of x. So y is equal to log to the base 2 of x. So this is how we are writing the inverse in log form. And if you think about it, what is, in its simplest form, a logarithm is just an exponent. Because you can see here that y is equal to log base 2 of x, so that is your logarithm. And where is the y? The y is here. That is your exponent. So in simplest terms, a logarithm is an exponent. For our purposes, we'll be using the logarithms to solve exponential equations. I mean, logarithms go back for hundreds of years and are used to simplify calculations, but for our purposes, we're just going to use it to solve exponential equations. So let's talk about some conversions. So let's look at this first. So let's say we had, so a to the x is equal to y. Well, in logarithmic form, that's going to be log to base a of y is equal to x, writing that in log form. So if I had this example, log base 4 of 64 is equal to 3, if I want to put that in exponential form, just abbreviate that there, that is going to be 4 to the third is equal to 64. Again, so here is our a value. Here's our a value, which is right here at your base. Then we have x, the x value, that is here. And again, it's matching it up there. Probably should have did it on the other one too. And let's use green. And then of course we have y, which is our 64 here. So you can see how that matches up to go back and forth from log to exponential form. So let's do that now. Let's say we have this exponential and we want to write it in log form. So that's going to be log to base 6 of 1 over 36 is equal to -2. So hopefully that will help just showing how to go back and forth between those two forms. Now there are two special logs I want to talk about. We have what's called the common log, and that is simply log base 10 of x, which is equal to y. And sometimes you'll see, especially in the calculator, as just log x. So in other words, this exponent, and that's the base here, is not written like you see it here, because it's just assumed that it is the common log, which is base 10. Common log, because base 10 is our number system. And that, if you're looking at it in your exponential form, it is just 10 to the y is equal to x, if you're just looking at it in terms of your exponential form. Then what we have what's called the natural log. Now, if you remember when we did exponentials, we talked about the natural base. Well, that is log base e, the natural base of x is equal to y, which we write as ln of x. So notice how we're doing that here. because that's how you're going to see it. You really won't see it as log to base e. You're going to see it as ln. That's what we use for natural log. So you got to get used to that, that notation. And that is just e to the y is equal to x if you're thinking of it in exponential form. All right. So let's do some of these in some conversions with the common natural log. So let's say we have ln of 4 is equal to 1.386 repeating, or not repeating but going on forever, because it's irrational. Now remember that this means log base e of 4, which is 1.386. So remember that that's just log to base e of 1.386, and that keeps going on forever. So if I was going to put this in exponential form, that is going to be e raised to the 1.386 going on forever, dot, 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 and that's going to equal 4. And you could key this into your calculator if you weren't sure. If you were to put this value in here, e raised to the 1.386, you would see it's going to be really close to 4. It's not going to equal 4 because the exponent here is irrational, but it'll be really, really close to 4. Then let's go the other way. Let's say we have e to the third is equal to 20.0855. Again, just a dot, dot going on there. So the log form would be log to base e 20.0855, which is equal to 3. But remember, you're not going to see it this way, so we're going to say it's ln 20.0855 is equal to 3. So again, you really won't see a log to base e. I can almost guarantee you it's going to be written as ln. All right, so let's talk about some properties of exponents. Let's talk about some of the properties. And the properties come directly from the definition of the logarithmic functions with a base of a. So it's really just coming from the definition that I just talked about. So let me show you this. So let's say we have log base a of 1. Well, that's going to equal 0 because a to the 0 is equal to 1. If I do that with the natural log, ln of 1 is equal to 0. That's because e to the 0 is equal to 1. And remember that, so you're not confused, ln of 1 is the same thing as saying log base e of 1, if that helps, if it's confusing you. All right, then we have log base a of a equals 1. That's because, I'll just quotes this, a to the first is equal to a, which of course is to the first power. And the same thing, if I have ln of e, that's going to equal 1 because e to the first is equal to e to the first. Then we have the inverse properties, which are extremely important, and these we're going to use to solve the exponentials. So we have log base a of a to the x, that is going to equal x. And if we have a raised to the log base a of x, that is also equal to x. And the same goes true for the natural log. ln of e to the x is equal to x, and e to the ln of x is equal to x. And again, these are the inverse properties, which you will definitely see again when we're solving log and exponential equations. And then the fourth, a one-to-one property. So if you have log base a of x is equal to log base a of y, well then x has to equal y, one-to-one property. And the same thing if you had ln of x is equal to ln of y, then x is equal to y. And again, that's just a one-to-one property. So let's look at a couple of examples based on the definition and the properties of logs. So let's say we have log base 2 of x is equal to log base 2 of 3. Well, then what is the x value? Well, x is going to be 3, and that's just based on the one-to-one property that we just talked about. So you can see that's where we get the x equals 3. To log to the same base means that this has to equal that. Then if we have this, so log the base 4 of 4 is equal to x, well, that means x has to equal 1, because you got 4 to the x is equal to 4. Writing in exponential form, we know there's a 1 here, so obviously these two have to be equal. All right, how about this one? Let's say we have log base 2 of x is equal to -3. Well, that means that 2 to the -3 is equal to x if we write that in exponential form, which of course we know that 2 to the -3 means 1 over 2 to the 3rd. And then we can simplify 1 over 2 to the 3rd. That's equal to 1/8. So x is equal to 1/8. And we'll look at one more, and it'll be a good variety for an introduction to logs. So let's say we have y is equal to log base 9 of 27. Well, if I write that in exponential form, I get 9 raised to the y is equal to 27. Well, that's not so clear about what the answer is. How are we going to get 27? Like what exponent, what value of y is going to make the left side equal to right side? But maybe you notice that I can rewrite these two. I can say that 9 is 3 squared, and 27 is 3 to the 3rd. Now what did I do? Now I have the same base. So this, I'll bring it down here, is 3 to the 2y is equal to 3 to the 3rd. Because properties of exponents, you would multiply those. Well, since I have the same base here, and they're being raised to an exponent, that means that this must be equal to this exponent in order for that to be true. So I can just set up that little equation there and say 2y is equal to 3, divide by 2, and I get y is equal to 3/2. Which of course you can check. If you say 9 raised to the 3/2, that is going to equal 27, which it does. All right, well, hopefully this helped you with the introduction to logarithms. And next we'll learn about the change of base formula, and then properties of logs that will enable us to expand and condense log expressions. So I will see you